Shani, I believe that's how you pronounce your name. Yeah, I'm Jacobus. As I say, I'm going to work on the board. Yeah, I thought that works nicely. I hope you can hear what I say, and I hope you can see what goes on. Yeah, okay. So, magnetic field diagrams. So the idea with like a magnetic field is that it is independent of, well, it only depends on how far away you are from the magnetic field. It's like gravity, you know, like the Earth. How farther away you are from the Earth, how the less force the Earth has on you. Because if you remember, it's F equals M. I don't know if you have done this yet, but usually you say F equals M times G, but this is just then the derivative. Can you actually see what I'm writing there? Okay, yeah. So F equals M times G. So usually what you would say is F equals mass 1 times mass 2 divided by the radius between you and the Earth, center of gravity squared. So then you see the further away you are from the center of the Earth, the higher this term below comes, and the less strong the force that's actually acting on you becomes. I wonder if I can actually zoom in. Can I? Oh, that's it. Doesn't seem like it. Right. What if I do something like this? I just need to sit nicely. Sorry. I think that works better. Yeah, okay, I'm just going to work with black as well. Yeah, okay. So, if you have a mass like the Earth, for example, let's say this is the Earth, yeah, you can see that, then the force field for the Earth, which is analogous to that of a magnetic field, just it looks like this. Just pulls you directly inward, okay? Because you're always falling towards the middle of the Earth, okay? Yeah, because this rule applies. Now, for magnetic fields, it works a bit differently. Just take this away. So for magnetic fields, the idea is also that if you are in a certain position in magnetic field, so with the Earth, it's like you're in the Earth's gravitational field, and then if you are in that gravitational field, you are going to behave in a certain way due to the force of gravity. So you're always going to fall inwards towards the Earth. Now for a magnetic field, that's quite different. So what happens is you have a magnet. You'll usually see when they make magnets, they split them in two with a line like this. And then they say this is the North Pole and this is the South Pole. Okay. Now also, it's just important to know that they call the one side the North Pole and the other side the South Pole. But the reason is just like convention. They could have called the North Pole anything. They could have called it like flowering pole and pot pole or something like that. Doesn't matter. They just decided when they discovered these magnetic fields to call the one side the North Pole and the other side the South Pole. Okay. So what happens in a magnetic field is if you are either iron or cobalt, nickel, or I think it's cobalt or cobalt. That's how I have it. These are the ferromagnetic materials. They call it ferromagnetic. And the reason is that all magnetic materials usually consist of an alloy that has iron in it, and then nickel and cobalt, they are also, if they are placed in a magnetic field, they will react in a certain way. And I can describe the way that they will react with my magnetic field diagram, which is analogous to a gravitational field diagram where you'll fall inwards to the mass of the Earth, you'll fall inwards. With a magnetic field, you'll act in a certain way, and that way is your magnetic field starts in the North Pole, and then it goes towards the South Pole. But and then you draw these arrows to indicate the direction. You can draw 1 or 2 arrows or 3 arrows per like line that you make. But yeah, it always goes from the North Pole towards the South Pole. So let's say I put a bar of iron over here. Okay, what will happen is the iron will move along this line towards the South Pole, if that makes sense. It's quite cool actually. So then, and this is just being one line. So you know, on a gravitational, like on the Earth, there's a bunch of, like if I'm over here, I'll fall to the Earth. If I'm over here, I'll fall to the Earth. It's the same with magnetic fields. You have a bunch of these lines that goes from the North Pole to the South Pole. To the North Pole to the South Pole. And then from the North Pole to the South Pole. From the North Pole to the South Pole. From the North Pole to the South Pole. Then you just need to draw your line, draw your arrows indicating direction. And then, yeah, that's how your magnetic field diagram looks. I'm not sure whether you can see it on that. I think you can. Let me just like bring it a bit closer for you, like this. Yeah, so this is how it looks. So you see, you start with points on the North Pole, just bring them around towards the South Pole. And the reason is a magnetic field. What happens is you start at a point, and then if I place anything, let's say I place some iron on this line over here, what will happen is the iron will move towards the South Pole. That's what these arrows show you. If I place a piece of iron over there, the iron will move to the South Pole. That's also how compasses work, but I'll get to that now. Put this back over here. See if that works. Wonder if I put like this. Okay, let's continue. Yeah, so this is how our basic magnetic field looks. So the first thing you need to note is that lines never cross. Lines never cross. And that's also the same on the Earth. You, when we draw the Earth over there, and we have all of our lines going inwards towards the Earth, the reason your lines never cross is because when I fall down towards the Earth, I fall in a straight line towards the Earth. I don't do something like this, I just fall straight. So if I start from this point, there's only one line that I can follow down towards the Earth. And that's the same for point over here, doop. And those two lines, they don't cross, otherwise you get weird, funky behavior that can possibly happen. But that's the same with the magnetic field. A magnetic field, it looks different than the straight lines of the Earth, because you have this motion from the north towards the South Pole. Okay? But the lines come across, otherwise you're going to get funky behavior that's even funkier than what you already have over here. So lines never cross. And then also, another thing to remember is that these are three-dimensional. 3D. So what I mean by that is, let's say, I'm going to try to draw a 3D thing, hopefully it works. Let's say I have a, just going to move to blue because my black's busy running now. Say I have a magnet that looks like this. So three-dimensional, let's say this is my North Pole, this is my South Pole. That's the other thing you need to remember. Magnetic fields always go from north to south. So you'll see it starts at north, then I draw my arrows, then it goes to south. So it goes out of the North Pole, there's a bunch of lines coming out, and then it goes into the South Pole, a bunch of lines coming in. So also see, in the North Pole I have 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6, but then like they spread out and then they concentrate again at the poles, because everything starts at the pole, but then they need to spread out over the entire space. So it's more concentrated at the pole, and that also means another thing that I need to write down for you here. The more concentrated the lines, the stronger the field. Let's the stronger the field. And this also makes intuitive sense. If I put something close to a magnet, like the piece of iron, it's going to be pulled stronger, and when I put it far away, it's not even going to be pulled. So because all my fields are concentrated at the North Pole, and they come out and they spread out around space, and then they concentrate back again at the South Pole. At my North and South Pole, the magnet is the strongest because there are the most field lines over there. Yeah. So let's come back to the three-dimensional thing that I drew over here. So what will happen is I'll have a line that comes from the North Pole towards the South Pole, from the North Pole towards the South Pole, from the North Pole towards the South Pole. I'm not sure whether this is nice, but you get the idea. It's three-dimensional. So in round. Usually when we draw it, just draw it two-dimensional, but yeah. Can you see that? Yes. Okay. So yeah, three-dimensional. Yeah, that's just something important that you need to know about magnetic field diagrams. So let's just get into a bunch of examples. I think that can work nicely. I can actually just move over to that side of the board. Oh, scheiße. Sorry. Okay, let's see. So I'm just gonna keep these notes over here. Then I'll take a picture of the board for you at the end as well, so that you can look nicely, because I'm not sure whether you can see that nicely, because I'm standing. I'll try next time to put the phone closer to the board. Yeah, okay. So let's start with just some examples of magnetic field diagrams. So the first one that we already did, but let's just do it again, is there's your magnet. Now they define the North Pole and the South Pole for the magnet, okay? And then you have your lines going from north to south, concentrated from the North Pole, spreading out, concentrated to the South Pole. So I start at the North Pole and then I draw, and also remember your lines can never intersect, because gravitational lines, you fall straight down, it's the same. It's the same analogy. Then you need to draw a small arrow pointing the direction of the field. And then you also start at the North Pole and you go out and then in towards the South Pole. Then you start at the North Pole, you go out and then in towards the South Pole. You can put your arrow anywhere on that line, though, okay. You start at the North Pole, you go out, you go in toward the South Pole. Okay, now let's start with the other side. So North Pole, South Pole, North Pole connected to the South Pole, North Pole connected to the South Pole, and then our last line, say, boop. And you can keep on drawing these lines, and you can keep on drawing them out to infinity, actually, because technically, if you have one magnet, that magnet's magnetic field spreads out across the entire universe, just like if I have the Earth's gravitational field spreads out across the entire universe. But there's a point where the force exerted by that magnetic field is so small, because the lines are so spread out, because remember when they are concentrated they are strong. The lines are so spread out, the force is so small that it doesn't have an impact on anything anymore. If I have my magnet and I put my piece of iron over here and it's not pulled by the magnet, then I know I still have magnetic field over there. It's just so weak that it doesn't do anything. That's like when I go into orbit on Earth, and I go out and out and out. At some point you escape Earth's gravity. You don't really escape it. It's still exerted on you. It's just, it's so weak you aren't really pulled by it anymore. And then the reason is because the force from the magnetic field is directly proportional. So you remember this alpha symbol means directly proportional to 1 over the distance from the magnetic field squared. So the idea is the further I am away, so the r is beneath the line, the further I am away, the smaller 1 over r squared becomes. So let's see, let's say I'm 1 meter away from the magnetic field, then that's 1, because 1 over 1 squared is 1. So the force is some constant multiplied by 1. Now, let's I'm 2 meters away from the magnetic field, then the force is equal to 1 over 2 squared, which is 1 over 4, which means the force is smaller than when I was closer. That makes sense. So this, I believe you should have seen this directly proportional symbol. It basically just means if I make a graph, force against 1 over r squared, I get a straight line. Yeah. And because it's 1 over r squared, I can also make this graph force against r squared, and this will give me a hyperbola. And then you'll see the further I am out away, the smaller the force gets, which is, I don't know, that's quite cool for me. Okay. So this is one example of a magnetic field. The other thing you'll see is they have like those horseshoe magnetic magnets that look like this. I'm going to try to draw it the best I can, but we'll see. And then your one side is north, your other side is south, and then you can draw a line like over there just to indicate that north and south. Okay, now what happens? So basic principles all stay the same. My magnetic field moves from the north pole towards the south pole. So I'm just going to start drawing lines, starting from the north pole, working towards the south pole. So north pole, south pole, line. North pole, south pole, line. North pole, south pole, line. Okay, so it goes like this, and then it also goes like this, north pole, south pole, north pole, south pole, north pole, south pole. Okay, you get the idea. Now what also happens is north pole, and then it goes around to the south pole, then north pole, which goes around to the south pole, and then which goes around. Just like you'll see my lines are really like ugly, but just when you draw them in a testing exam, just make sure that they don't actually cross each other, and that also that they are concentrated near to the pole. So you'll see over here there's like a lot of lines, and over here there's not a lot of lines, which means it's concentrated at the poles. Yeah, so that is how I think you call it a horseshoe magnet. That's how a horseshoe magnet would look like. If you were asked, I was never ever asked to draw it. I was always just asked to draw just a normal magnet. And okay, now I just remembered. So that is just for a single magnet. But what happens when you get two magnets and you push them together? I remember that now. Okay, so let's start with that. Two magnets pushing together. So the principle stays exactly the same. Concentrated at the north pole, going out, spreading out across space, concentrated at the south pole, and they move from the north pole towards the south pole. So let's start with magnet number 1, magnet number 2, north pole, south pole. Let's make it south and north. So what I'm doing in this case is I have my north pole pointing to my south pole, my north pole together. So I don't know if you've ever played with magnets before, but when you do, you'll find it's really like it's weird, because when you have two magnets, you'll find that two sides attract each other usually, but then when you turn the one around, they like repel each other. It's really fun to play with. I actually wonder if I don't have any magnets with me now. Sometime I'll get and I'll make a video if you haven't played with them before, but I believe you would have. Like they attract each other when it's north and south pole, because north and south pole attract each other. So they attract each other, but then if you twist it and it's north pole and north pole, they repel each other. It's really difficult. Like when you put them together, they jump out of each other with force. So what happens is the magnetic fields in this case is, firstly you can just start with your normal magnet, because you know how your normal magnet will look. So you start from the north, go towards the south, start from the north, go towards the south, north, south, north, south. Okay, that's nice. nice way to start, just north, south. And the same with this one, north, north, south, north to south, north, south. I'm not going to draw so many lines. You don't actually have to draw that much lines. And then you just indicate the directions as well. And now, to start with the interaction that actually happens between the two magnets. So, North Pole attracts South Pole. Doesn't matter which magnet you're on. So what you'll do is you'll just draw lines that goes towards the north to south, and then you can like make them bendy, so it looks like they are like spreading out across space. So that's why this line we can make shape. This line we're going to make a bit more like bendy, like this. You'll see, like they spread out across space. Let's say, and then you just draw your arrows pointing from north to south, and then you can also like make some lines that go like this, north to south. Oh wait, that's the wrong direction. Oh, sorry about that. So north to south, this, and then on this side it as well. Also, just another point, which is also on the line, should never touch each other. When you draw your lines originating out of one of your poles, make sure that they don't touch each other over there. Like you'll see over here where I drew this line, it accidentally touched one of the other lines. Just so what I would recommend is first draw them in pencil, and then when you see nothing touches each other in the origin, each one starts at its own point. Then take your pen and draw with your pen as well. Then I don't know, it just works nicely. I think, yeah. So this is the one case for two magnets coming together. Let's see. I think I can work over there probably. Yeah, let's work over there. We can still see over there. So the other case is where you have two north poles coming. So south pole, they attract each other because north and south attract each other. And then with the north pole, you have one, two. Let's say this is the north pole, and the south pole, Okay, so the north poles repulse each other, and the reason they repulse each other is, I'm not actually sure why though. Yeah, probably when you look at the force, you'll still do that, the force of a magnetic field, but north and south attract each other, south and south repulse, north and north repulse. So when I draw these, I'm just going to start drawing normally, connecting my north and south for each of the poles. Okay. North and south for each of the poles. Okay, and then what happens is you can draw your lines outwards like this, and then they repulse each other. I'm not sure whether this repulsion is clear, but they really like repulse each other, like push each other away from each other. And then I just remember to put your lines your arrows indicating direction of the fields. Like that. Now, I'll also take a photo of close view. Yeah, and then I wonder, can I work over there? Yes, I can. Okay, let's see. So this is north and north, and then south and south is exactly the same as north and north. So I'll quickly do them for you, but you'll see it's exactly the same, because south and south also repulse each other. So it says south, south, north, north. Just going to draw my lines. I'm just going to draw just a few of them, just to get the idea. So they repulse each other, repulse each other, and then from north to south, so just indicate the direction. So the only difference between north and south is the direction of the actual fields. Now what does this mean? So what does this magnetic fields mean? Remember when I talked about the earth, and I was like, if you're falling down towards the earth, you're falling in a straight line, and if you're over here, you can make a drawing of the earth with all of the lines going inwards, which shows the direction of the gravitational field. That's the same for the magnetic field diagrams. So let's say I take some iron or nickel or cobalt, because they are the ferromagnetic materials, or just magnetic materials. I think actually in your textbook there is an explanation on why they are ferromagnetic. I can explain that for you as well if you want to, because I also know why. I believe I know why. It's quite interesting. Okay, but anyway, let's say a piece of that, and I put it somewhere in this field. So let's say the blue represents a piece of iron, and the piece of iron I put over here, boom, in my magnetic field. What will happen to that piece of iron? That piece of iron will follow the line, and it will go towards the south pole. That's what will happen. That the field line with the arrow exactly explains what will happen. Let's say I have a piece of iron and I put it over there. What will happen? The piece will move along this line towards the south pole. Okay, now let's think about this magnet system over here. So let's put a piece of iron right over there. Oh yes. So I understand is that piece of iron will zoom towards the south pole. Yeah, that's basically how it will orient itself to point towards the south pole. Yeah, so just like you follow the magnetic lines. I'm not actually sure whether that's correct, but that's how I understand it, and I read through through school, so I think it's fine. Yeah. Oh, and then there's also this just the Earth's south and north poles that you're supposed to work on. Yeah, I'm just wondering. Do I have place on my board? Okay, I think I have an idea. I'll quickly explain that and then make a big picture for you. Put this like. And now I can see my fridge. Okay, over here. So, the next section. Oh, let's quickly do a funky example first. I think that's funny. So let's say we have a magnet, and a magnet. So we have three magnets. Three magnets being. Can you see over there? Yeah. Okay, so let's say one is a south. Oh, my black is busy running out. That's so sad. So one is a south, and one is north. Okay. So let's say we need to draw this magnetic field. So it's going to be quite funky. I've never gotten one of these, but if you can do this, you really understand the work. And then we have north, and then north. Okay. So what will happen is I'll start just like drawing. So let's just start with each magnet. So now it goes from north to south, from north to south, north to south, north to south. Incidentally, that's supposed to be the south. North to south. Okay, now let's try to figure out what interactions will happen inside this area in the middle. So, I know that my magnetic field goes from north to south. So that's what I'm going to start with. I'm going to make my north goes to south, north goes to south. I just like try to spread them out, if that makes sense. North goes to south. So you see my north goes towards my south. And now what also happens is my south repulses each other. So I get like this repulsion happening over here. These lines going in over there. Now, that's quite confusing, but I don't know, it's quite funky. And then the last thing that I just quickly want to do with you is what is how much is for the Earth. So let's quickly do the Earth as well. So let's say this is the Earth. So you know that the Earth's north pole sits over there, let's say. Did you see that catch? That was amazing. Let's say the Earth's north pole is over there, so and then that's supposed to be there, so let's say that's the south pole. Okay. So, north and south of the Earth, okay.
So you remember what I said about like put a piece of iron inside a magnetic field, it will like go towards the south because that's the direction that the magnetic field points in. So a compass, which is quite cool, it's like a compass is basically just a piece of string and then I put a piece of iron on that string, and then that compass, when it interacts with the magnetic field, it will orient itself in the direction of the magnetic field. So on Earth, you know that a compass always points north. So the compass on its string, and then it points itself towards in the direction of the magnetic field. So on Earth, because the compass points north when I put it in, the magnetic field on Earth, it goes like this. Because the Earth, you know that the Earth has a like ferromagnetic, it points towards north. Let's make that north. So you know that the Earth has like a center in the middle made of iron, liquid iron, nickel and stuff like that. That actually causes a magnetic field, the Earth to be a big magnet as well. So the Earth also has these magnetic fields, and then when I put the compass, let's say I put this thing inside the magnetic field, let's say over there. I say. Now what happens is that thing will orientate itself. So it will spin until it points in the direction of the magnetic field that it is in. Yeah. Now, this is where it gets like funk and confusing. Because you remember that I told you that magnetic fields always point from north to south. So if I have a magnet like this, it always points from north to south, from north to south. Okay? Now the thing is, on the Earth I have my south and my north, but it points from south towards north, which is quite confusing to think about. So basically what happened is some physicist or somebody somewhere made a bit of a F up when they like named the north and the south poles for the magnets, and now what happens is on Earth we have our magnetic pole pointing from geographic south to geographic north, so what they needed to do then is they called the South Pole. So you know there's geographic south, but magnetic north. And then the North Pole is known as geographic north, okay, and magnetic south. I must say, yeah. And the reason, so it's known as geographic south because that's just how they decided it's supposed to be south pole. But it's known as Earth's magnetic north pole because the magnetic field originates there, points out and goes in towards south. And then the same, so that's geographic north, but it's known as the Earth's magnetic south pole because it goes in there. And then also, one other thing that I remember is, you know the Aurora Borealis, the Northern Lights, Aurora Borealis, and then the Aurora Australis, I think. Oh, my black. Aurora Australis. Or something like that, I'm not really sure, but it will be in your textbook. So what happens is, particles from the sun and from outer space, there are a lot of them, like to space, like electrons and photons and stuff like that. They interact with Earth's magnetic field. But you remember what I told you about, like, it's a magnet is the most concentrated at the North and South Pole because it starts at the North Pole and then it spreads out across space and then it concentrates back in the South Pole. That's the same with the Earth. So on Earth, my magnetic fields are most concentrated in the North Pole where they go in, and most concentrated in the South Pole. Well, the geographic South Pole, the magnetic North Pole where they go out. So what happens is these particles interact with the magnetic field, and then because the magnetic field is so concentrated at the North Pole, it creates these nice green lights and northern lights, and then the same happens in the South Pole where you get the southern lights. Yeah, I don't know, it's just really funky. Yeah. Okay, well, now that's basically it for magnetic diagrams. Yeah, you can send me a few questions on the work if you want to, and also I can help you in making videos for that and stuff like that. Yeah, so I hope this helps. I'll take a picture of the note as well and send it to you. Yeah, cheers, bye bye.